So last time we got a look at energy principles which are inherent in mechanical problems that we've considered so far. So what was the aim of the last lecture? Well, I told you that in the past we've studied problems like this where we have m times dv by dt, which is the inertia term in our Newton's equations of motion. And then on the right we have a resultant force. Okay, so this is a resultant force, a sum of forces that acts on an object. And by Newton's second law, the resultant force is equal to the inertia force here, which is the mass of an object, times its acceleration, which is dv by dt, and here v is the velocity vector, so this is dv by dt is velocity vector of the particle. Okay, so what we said was then we had some energy conservation. Which basically says, okay, with such a problem, we can write a energy balance equation. And we derive this directly from the governing equation for the motion of the object. So we have this capital T plus V equals E. Just a quick recap, this was kinetic energy, KE, kinetic energy. Now, sometimes as we go through examples, I will not derive this continuously. Okay, so I'll derive it a few more times and then I'll stop doing this, because kinetic energy is the energy that an object has due to the object's speed and the object's mass. And it comes from the inertia term. So it comes from playing with the inertia term. If you look at how we derive this. On the other hand, we had this quantity known as PE, not physical education, but potential energy. Okay. And this we've seen depends on F, the resultant force, and also on the position. Okay, and this is characterized by R. Remember, we use this when we talk about kinematic quantities R. In fact, for a constant force, i.e. a constant vector F, we showed V is equal to minus F dot R. Okay, remember that R is the position vector that has the following description in terms of x, y, and z, the functions describing the principal displacements of the particle. Lastly, I told you about this. This is the total energy. It's a constant, and we can grab this constant from initial conditions. Okay, and what happens is, or as you'll see in examples, that T and V, so this is an aside note, T and V can vary at the expense of the other. Why? Because their sum should be constant. And equal to capital E. Now, this is important because this shows us how mechanical energy can transfer. So if I increase my kinetic energy, which I can do by going faster, then something has to happen to my potential energy in order for the and total energy in the system to be conserved, in order for E to remain constant when I add my potential energy to my kinetic energy. And there is this in mechanical problems, this exchange process going on between these two energies, and a change in kinetic energy causes a change in potential energy naturally, because if you have some speed, okay, obviously you're changing your position, and then this can influence your potential energy, and vice versa. Okay, so that was just a quick recap. That was the recap. Now let's get into a question where I'll use the results. I'll use the results, but I'll also derive them again, just for the sake of answering the question. So, okay, given this example, it says a mass of 0.2 kilograms travels through a force field. Okay, this we're going to look at in the next section, which is on position-dependent forces. Basically, if you have a force field which depends on your position, or could be constant acting force, then you're said to be subjected to a force field. And this force field is described by this vector here. We all know how to read this vector. And this is defined with respect to some reference system. Okay, I'll draw all this on a diagram, in fact, now. So you have a scenario like this. It's a 2D motion. Here's your particle. Okay, and we'll call this P. And your particle is moving in some way through the space defined by xy with the reference system, reference point O. Okay, on the other hand, we have a vector. Let's draw this accurately. It could be, without loss of generality, it could have any direction, but it just happens to have this kind of direction. Probably a little steeper would be better. There we go. So this force acts sort of in this direction. Okay, so this is minus I plus 3J. Okay, newtons. And it says initially our particle is traveling along the horizontal. So this means that the position vector that characterizes the position of our particle when time t equals 0, so this is t equals 0, it's said to be traveling along the horizontal axis, so that's x. So here we're told it's located at a distance 4 meters from O. Okay, I think it should be it should be located at or displaced 4 meters from O, so at least we have an indication of the direction. So let's just for argument's sake, let this 4 be over here. So okay, so we can say okay, so located or displaced, because this tells us displaced 4 meters from O. This tells us the direction with respect to O that we measure the distance. So let it be, this is our initial position. So 4 along the horizontal axis, we need to represent this position as a vector, so that's 4 times I. And then, of course, it says that we have a velocity initially of 2 meters per second. So, of course, it's moving along the horizontal in this direction. And so its velocity along the horizontal axis is 2 I. Okay, so this is meters per second. Okay, so it doesn't have a vertical component of velocity. The key word here is along the horizontal. Okay, so with this, we're ready to find out how to grab hold of the potential energy of the particle. This is the first thing we have to do. Now, notice that we've been told to then grab total energy of the particle, and then the kinetic energy and the speed of the particle at this point. Okay, so first of all, what I'm going to do is I'm going to say first, note F is constant. Okay, so this means its potential energy is minus F dot R, which is, and I'll derive this from scratch, which is minus I plus 3J dot, now what's R? R is Xi plus Yj plus Zk. Don't confuse it with what I've wrote at the above because this is the initial conditions. Okay, so with this in hand, what I can do is I can clearly construct the dot product. So that is minus 3x. And so then this has no k component, so I don't have to worry about the dot product with this k component. So what I will have to do is though dot the j's, so 3y. Sorry, I got the numbers wrong. It's this. Okay, so in other words, this is our potential energy. Of course, T is just 1/2 m modulus of V square. Okay, V is Vx I plus Vy j plus Vzk. Note, also I drew this as a 2D problem, so object moves in the plane. And this means that I don't have to worry about these guys corresponding to k. They can just be taken as 0 for without loss of generality. So, okay, very good. So this just means I have dx by dt, I plus dy by dt, j plus dz by dt, k. Right, okay, so we know that T plus V equals E. So this means we have a relationship like this. Now I'm going to substitute in V equals some constant. Now, I'm going to derive this from scratch. Now, we've just done it there. We just jumped all the steps. But I'm going to go from scratch anyway and just show you how this would have come about. So next, let's remind ourselves how to get this. So sometimes it's more important in mathematics to not remember a result, but to remember how you obtain the result. And this is particularly important because it helps problem solving. Okay, so how am I going to do this? So we need to do this, write Newton's equation of motion. So I have dm. Notice I haven't used the fact that m is 0.2 kilograms yet. So I write down Newton's equation of motion like this. Okay, m's a constant. So take dot product. With v, and we get this, v dot equals f dot v. Now, next, we know, because we showed it last time, that this is 1/2 d by dt of the modulus of v square. If you're not sure why, have a look back at the last video, and this will explain why. Okay, so we have on the left 1/2 m d by dt modulus v square equals f dot v. Now, remember, I can then integrate with respect to t. And what I'll get is, I'll get integral. Now, because m is a constant, and 1/2 is obviously a constant, this is clearly 1/2, which is exactly our kinetic energy term, is equal to integral. Now remember, I mentioned something about this being the work done by a force. Interesting point, this is commonly associated with work done by your force. Okay. Now, work done, I'm going to talk over this for a second before I write any more. Interesting thing about work done is by definition, if the force doesn't move an object, then it doesn't do any work. Okay, so you might consider when you do. So this is by the definition of work done in physics. So you might consider going to the gym, and you might take a great big weight and hold this above your head. Say, God knows why, but let's imagine you're doing some exercise. And you hold this weight in position. Okay? You hold it in the same position over some period of time. Then, of course, you're applying a force in order to keep the weight above your head. But if according to the definition of work done, if this weight remains in the same position, the force that you're applying to keep this weight above your head says that it's doing no work. Of course, you might feel the strain of all of this as you do it. But in terms of the setting of mechanics, any force that creates any force that makes a particle move through some distance does work. If it doesn't do work, it's because the force is unable to move the object. Okay, so this is the work done. Of course, this is one other thing. You remember I expanded this out. Now remember this right hand side is minus I plus 3j. And I have to dot this with, and I'll just expand this out. Of course, this is again unnecessary, but let's go with it. So what I have is, after the dot product, I have minus Vx as the first component. Then in fact, you know what? I'm going to skip a few steps. So minus Vx dt plus integral of 3 Vy dt. Okay. Now, remember that x dx by dt is Vx and dy by dt is Vy. So this allows us to, if you will, use the chain rule. So this then gives us this. You have to integrate minus 1 with respect to dx. And then we have to integrate 3 with respect to dy. So this just gives us a real easy integration, minus x plus 3y. And this is precisely minus our potential energy, V. Okay, so, right, let me write down then, therefore, what we have shown that our mechanical problem gives us the following energy conservation principle, 1/2 m modulus V square. Now, there was a problem here because your naughty lecturer didn't put down the constant, arbitrary constant of integration, because I did an indefinite integration. And moreover, just for argument's sake, we're going to call this C. Okay, so effectively, if I just move the terms with x and y onto the left hand side, I get this equals A. Perfect. And this is exactly what we had. So that's just a recap. In future, I'm not going to bother doing all this stuff. I'll just go straight in and use the formulae. I won't derive it. Good. So now with this in place, so this is our energy principle. Of course, by the way, this was the answer to the first part. The total energy for the particle we're coming to now. So this, let me just cordon this off. That's your potential energy, V. Okay. 2, we're looking at total energy. So we know this is the total energy. But we're told find the total energy. What is it? Well, how are we going to find it? Remember the initial conditions. Let me go back and grab these. So the initial conditions read like this. And this is how we're going to get hold of the constants. Okay, this is our initial conditions because the object moves horizontally. So this implies in terms of x's and y's, so this implies x of 0 is 4. I'm looking at the first one. So this is 1, this is 2. So this is 1 implies x of 0 is 4, y of 0 is 0. 2 implies what Vx of 0 is 2. Vy of 0 is 0. Okay. So how do we use this to our advantage? Well, in this, we can sub this in because this is valid for all t. So this energy principle, smiley face, is valid for all t. Okie doke. Well, remember that V is Vxi plus Vyj. So this implies that V of 0 is 2i plus 0j. And if I take the modulus of this is just an intermediate calculation. course, well, if I take the modulus squared, and then all I have to do is do the sum of squares of the components of v of 0. So, what this gives me, therefore, is 4. Okay, because it's equal to 2 square plus 0 square. And remember, I've got the square up here, so I don't need to take the square root. Okay, so let's see if we get this in smiley face. What we therefore have is when t is 0, we have this 1/2 m modulus v of 0 square, which we just computed, x of 0. Remember that these things are functions of t. So now I just sub in the values. Remember that m is 1/5, so I have 1/10 multiplied by 4. Plus, I'm just substituting values in, it's as simple as that. Remember, x of 0 now is 4. And now y of 0 is 0. Okay. Good. Excellent. Okay, so this implies that E is what? Well, it's 44/10, which is 22/5. Okay, that's your total energy. So total energy in the system, the constant total energy E is 22/5, and the units for this are Newton meters. Good. Now, what about the third step? Oh, come on. Find the kinetic energy and the speed of the particle when it reaches 3-2. So for this, we're just going to use the relationship that we picked up. So I'm going to take this, because this is valid for all t, and we're just going to plug in the values that we know. Okay, so this is for 3. Find kinetic energy. And speed. Okay. When object is has the coordinate p 3, 2. Let me just double check I got the numbers right. Yeah. Okay, well, very good. So object reaches, or particle reaches, this at time capital T, where it has the speed, or where it has the velocity vector. V of capital T. Okay, and it has the position, x of capital T is of course 3, because that's the position at the point, and y of capital T is 2. Wonderful. Now, this is, remember, this is KE. This is what we want first. So we want the KE at this time. Remember that this is now, the total energy is 22/5. So if we know this, we can clearly calculate the kinetic energy, and we do. So at T equals capital T, we have the kinetic energy is equal to E minus x of t plus 3y of t, which is 22/5 minus 3 plus 6. All right, and this is 22/5. This is, of course, now plus 3, which, if I multiply 3 in the top and bottom, by 5. Then I get 37 over 5 when I add those two together. Hence, kinetic energy, 1/2 of this quantity square equals 37 over 5. Now, what about speed? Well, we just need the absolute value of the velocity, which is v of t, and that comes straight from this equation, no problem. So this implies that if I just rearrange, remember that m is a tenth, so what we'll do is we'll just write this. Two over m, okay? And this is now multiplied by 37 over 5. So now with m is 1/5. We have 10, clearly, multiplied by 37 over 5, which is 2 times 37, which is 74 meters per second. That's the speed of the particle. Okay, so that's it. So as you can see, knowing something about the energy for a system is very important, as it does allow us to extract some very important information about the behaviour of objects. Notice we don't know how exactly x and y change in time, but we can say something about the speed, and we can say some things about the total energy a particle has, which is not directly characterizing the motion of an object. Okay, so that was this question answered. When we come back, we'll have a look at a different example where we have a particle that goes down a slope. So thanks very much for your attention. See you next time. Okay, just a quick note about the end of this last example. I did finish it too quickly. We actually calculated the speed squared, so what we just need to do is remember you need to take the square root of the final answer, and this will give you the value of square root of 74 meters per second as the value for the speed. Okay, that's all. See ya.